Chapter 5, Electrons in Atoms. And this is section 5.1, Models of the Atom. Here's the objectives. And I want you to put these in your notes because I'm going to want you to use them later on. So write these down. Identify the inadequacies of the Rutherford model. Identify Bohr's proposal. Describe the energies and positions of electrons according to the quantum mechanical model, and describe the shapes of these different sublevels. Okay, so take a look in your book. Turn to page 128 in your book so you can see the different models of the atom. And you can see in 1803, the Dalton atom, and you can see that it was just a sphere, just the atom at the time. And then the next one is the Thomson model, where kind of the plum pudding idea, you've got the negative charges in there. And then along comes Rutherford's idea, and he's now talking about the nucleus and how electrons are moving around. And he's saying that they're moving around the nucleus of the atom, all around, moving. But the problem is with his particular model is it didn't do a very good job of explaining the chemical properties, why the atoms acted the way they did. So he's got a student named Niels Bohr who works with him, and Bohr comes out with a new model, and what he says is, well, these electrons are going around in paths, circular paths or orbits, kind of like the planets going around the sun. These electrons are going around the nucleus. But they have to be in certain fixed levels. They can't be in areas in between. So they could be in this level that's a certain distance from the nucleus, or they could jump out to one that's farther away, and so on. Can't be anywhere in between. Kind of think of it like if you're on a ladder, you can be on the first rung or the second rung or the third rung, but you can't be in between. So that's what he's talking about at this time. So it can't be between levels. And they can move from one level to the other. And in order to do that, they have to gain or lose just the right amount of energy. So in order to move from the inside level to an outside level, they'd have to gain some energy. You'd have to put that in there. And, when they want to drop back down, they're going to lose that amount of energy, what they call a quantum amount of energy. And when they're talking about that, they're talking about certain exact amounts, certain discrete amounts in order to move from one energy level to the other. And sometimes you've probably heard the term quantum leap. Well, what they're saying by that means that you're taking this big jump, you're going from one level to the next level by this energy that of the electron is said to be quantized. It's a certain exact amount. So the other interesting thing about it is when we're talking about these different levels, those levels are the amount of energy to change levels is not the same. So it doesn't take the same amount of energy to change it from level 1 to level 2 or level 2 to level 3. In fact, if you look at the picture on page 129 of the ladder, you see that it's got different lengths between the rungs. So kind of think of a ladder with, instead of being all the same, some of the rungs are closer together and some of the rungs are farther apart, and that's what they're talking about. It takes different amounts of energy to go between those. Now, the Bohr model worked really well for one element. It worked really well for hydrogen. It explained exactly how the electron worked for hydrogen and so on, but did not work for any of the others. Once you started adding more electrons, it kind of fell apart. So it's getting better. It explained properties of elements and things better than the Rutherford model, but still not very good. So then the current model is the quantum mechanical model proposed by Schrödinger back in 1926, and that's kind of the model that's been around now for quite a while, nearly 100 years, what we believe. And it's mostly just a mathematical equation. It talks about probabilities and where are you going to find the electron. So if the current model is called the quantum mechanical model, and what it says is that there are certain amounts, certain energies that are allowed, and you're going to find the electron in certain areas with certain probabilities. So what they usually say is, where you're going to find the electron with about a 90% probability. Think about it, if it was possible to you're taking just photos and you're just putting a dot everywhere, every second where the electron is, and eventually it's going to get kind of an area that's shaded in, and that's going to be kind of a fuzzy cloud, what you would get, where the electron is going to be 90% of the time. So it's going to be in there 90% of the time, 10% of the time it's going to be somewhere else. We don't know where, but that's where it's going to be. So probably the best example, think of like a fan. So if you got a fan blade and it's going around and around and around, the blade's in there. I mean, if you put a dot on a blade, it's in there. But you're just going to see kind of this blur, and you wouldn't know exactly where it was at any particular time. But you could say with pretty good probability, in fact for the fan, probably 100% probability, that it's going to be inside that particular area. So that's what they're kind of talking about when they're talking about these probabilities and so on. These different orbitals, these different atomic orbitals there are different orbitals that exist, and we designate those with letters. So the first one is S. So the S orbital is a sphere, and take a look on page 131, and up in the top you'll see a yellow sphere, and that's what they're talking about. In other words, that sphere, that shaded area, is where you would find the electron 90% of the time. And sometimes I think of like these orbitals as kind of like the room that they're going to be in, and they're in that room 90% of the time. 10% they go out the door and go somewhere else. And so, the S ones, they're spherical. Notice the blue ones to the right there, those are p orbitals, and those are dumbbell shaped. And there's actually 3 sets of them because it's kind of a 3-dimensional thing. You can kind of think of them, some of them as going left and right, some of them up and down, and the other ones, forward and backward. And you kind of would put all those together. So kind of think of that all kind of put together in on one thing. And that's where you're going to find the electrons if they're in the p orbital 90% of the time. So they're going to be in those areas. So that's a little bit different shape than the other ones. And then there's the d orbitals, and they're even different, weirder, I guess. And look on page 132, you'll see those. And you'll see these pictures of these, kind of double dumbbell shaped, or this one with looks like a donut and a dumbbell, and these are kind of some strange different areas, but once again, these are the areas where you're going to find the electron 90% of the time. So when they talk about the atomic orbital, what they're saying is it's this region of space, it's this area where you have a very high probability of finding the electron. But it's not always there. It's just there most of the time. And we have different levels, different energy levels in the atom, and they're usually called principal quantum, or we represent those with principal quantum numbers, which is n. We say, n is what we use for that. And we add different levels, 1, 2, 3, 4, 5, 6, 7, so on. The lowest one is 1, so n equals 1 is our lowest principal energy level. I kind of think of it like a hotel. So the principal energy level is like the floor. So the first level, the first floor, that's the lowest one, has one sub-level, and I kind of think of sub-levels as being like the rooms. So in the lowest floor, the lowest level, you have one room, one sub-level. And so the way that we indicate this in science is we write 1s, which stands for the first level, s sub-level. If we go to the second level, there's actually 2 sub-levels. There's the s and the p. Or if we want to do my hotel analogy, on the second floor there are 2 rooms, S room and P room. And so you got 2S and 2P. On the third level you got 3 rooms, or 3S, 3P, 3D sublevels. Notice that for every every level you have that many sublevels. So the fourth level has 4 sublevels, 4S, 4P, 4D, 4F. Okay, so that's what we're talking about there. Just whatever the principal quantum number, that's how many sublevels there are. There's also a nice little formula to figure out exactly how many electrons you can have and that is 2n squared. So, in the first level, think about it, we got 1 squared, that's 1, times 2, there's 2. So you can only fit 2 electrons in that first level. So the first floor of the hotel can only hold 2 electrons. Second floor, second level, 2 squared is 4, times 2 is 8. So it can hold 8. Third, 3 squared is 9, times 2 is 18, and so on. So just plug in the number, take times 2. Okay, so remember at the beginning I asked you to look at the objectives, and so what I want you to do is in your notes I want you to write down some of the inadequacies of the Rutherford atomic model. What was wrong with it? Why didn't they like it? Why did we change it? Okay, second one, I want you to talk a little bit, explain to me what the Bohr model was about. And the third thing, explain the energies and positions of electrons according to the quantum mechanical model. So explain to me in your words what the quantum mechanical model means so that we can talk about that. And then last, talk to me about the shapes of these different sublevels so that we can kind of go over all these things. This starts to get a little more complicated, and I want to make sure that you understand these objectives and the things that we're going to try to do here.